Let me introduce you to Sally. Sally was a healthy, normal elementary school child when she started to have symptoms of a stroke. Not knowing what was going on, her parents took her to the hospital and the doctors ordered imaging of her brain. And what they saw in her brain was a surprise to all of them. Sally, despite her young age, had blockage of some of the large arteries in her brain. In addition, she had changes in her brain that we expect to see in an 80-year-old stroke patient who's had decades of uncontrolled hypertension. But we never expect to see the changes in a child. So a neurologist can look at Sally and find out about her symptoms, look at the images of her brain, and start to try to treat her to prevent a massive stroke. But a physician who is a scientist can look at the big picture of Sally and realize how devastating this disease is, but then zoom in to the molecular level and ask why this happened to Sally. I am a physician scientist, and I want to tell you the story on how I found out what happened to Sally, even though I wasn't even working on strokes, the cause of strokes. And this is really a story how I use my clinical and research skills to figure it out. But more importantly, this is the stories of the patients who participate in my research. These are patients that they're looking for the answer as to why they have such a devastating disease. So for more years than I care to admit, I've been working on thoracic aortic aneurysms and acute aortic dissections. The aorta is the major artery coming out of your heart, and aneurysm is when that tube enlarges. And the natural history of an aneurysm is that it progressively enlarges over time, and it reaches a certain size and it becomes unstable. And sometimes it just ruptures, but more commonly, the blood goes from inside the inside of the artery and dissects into the wall and then tears the wall apart. And that's called an acute aortic dissection. It is a life-threatening condition. Half the people that have it die before they even make it to the hospital, and it's a medical emergency if they live long enough to make it to the hospital. We can change the outcome of this disease if we know who is predisposed to this condition. And because we can go in and surgically repair those aneurysms and prevent the dissections and prevent the premature deaths. Now, I and others have determined that these aneurysms and dissections can be inherited in families, just like breast cancer can be inherited in families due to BRCA1 and 2 mutations. But it's a little bit different for this disease because we found out there's many genes that can lead to a predisposition. And we want to find each and every one of them so we can figure out who's at risk. And John Ritter, a very well-known comedian and actor, he's an example of how it can run in a family. He died of an acute aortic dissection in his early 50s, and he was actually on the set of a sitcom when he had chest pain and had the dissection. His father was actually Tex Ritter, one of the Texas singing cowboys and an actor, and he may have died of an acute dissection also. After John's death, the family contacted me and I arranged for all of them to have imaging of their aorta. John's brother Tommy was found to have an aneurysm and went to surgery and was repaired, and Tommy is still alive and with us today. And that shows you the power of realizing a disease is running through a family and preventing further deaths. Here is a picture of a family, a pedigree of a family that has participated in my research studies. And just to make you all junior geneticists, the pedigree is actually just a family tree. And men are depicted as squares, no surprise, right, ladies? and women are circles. A connection between a square and a circle indicates a marriage, and then a line down shows the children. Now, when the symbol is filled in black, it means that individual is affected with a thoracic aneurysm and dissection. The diagonal line means that person has died. And you can do this kind of diagram with your own family to figure out what diseases you may be predisposed to. So you can see this family had multiple generations where it was passed from one generation to the next, and had the disease was passed from one generation to the next. We had figured out the genetic cause in this family, and we had called up the people at risk and said, you haven't inherited this risk, please go to your doctor and get imaging of your aorta. And shown up here is Tyler Cayley. He was a 19-year-old in this family. Between the time we informed him and before he could get into a doctor, he started to have chest pain. He went to an ER and said, I think I'm having an aortic dissection. My father had one, my uncle had one, and I think that's what I'm having. And they said, no. It's not inherited in families in somebody like you. And so he went to another ER, and yet a third ER, and all of them said no and sent him home. He went home after that last ER and died 3 hours later in his apartment of an acute aortic dissection. And this was devastating to his family, but it was also completely devastating to me because I was doing this work to prevent these deaths. And it made me realize that I need to take the responsibility of making sure the information gets out to the physicians and change the way we practice medicine. It wasn't enough for me to be doing the work in the lab or in the clinic, but I needed to get that out. So I partnered with Amy Yazbek, John Ritter's widow, and Deborah McMillan, Tyler's mother, and others to get the word out on acute aortic dissections. And we've come up with Ritter rules, which are the symptoms and risk factors for acute aortic dissections. I also talked to an editor at the Wall Street Journal to do an article on Tyler's family, which turned up on the front page of the Wall Street Journal. And this really helped a lot to get the word out. To be honest with you, I think more physicians read the Wall Street Journal than the New England Journal of Medicine. So let's get back to Sally. How did we find the gene for Sally? So this family here, another family where the disease was being passed from one generation to the next, actually called up Deborah McMillan after reading that article in the Wall Street Journal and said, who found the gene in your family? Because we want her to work on our family. They got in touch with my group, and I actually flew to where the family was to actually meet them because it was a large family with many affected individuals that were still alive, and it gave us a lot of power to find the gene. So I went there in an auditorium a little bit smaller than this one. I actually got up and talked about the disease and why we wanted to find the genes and what the informed consent was about. And then I said, are there any questions? And somebody in the family got up and said, well, there's a lot of people in our family that have had early onset coronary artery disease and heart attacks. In fact, another institution has already been here to collect blood from people with these heart attacks. And could it be the same gene? I said, no, I don't think so, because an aneurysm is an enlargement of an artery, and coronary artery disease is due to the fact the arteries become blocked and closed off. Two different processes. So I think it's two genes, bad genes in your family, and it's really good you're participating in this other study. Then I asked, can I just examine everybody who has survived an acute aortic dissection? And they actually pointed out to me that they all had this very distinctive rash all over their body. And it's a purplish net-like rash called livedo reticularis. And I thought, oh, that's interesting. But it wasn't until I got on the plane and was sort of dozing off, and I was thinking, livedo reticularis, that I actually remembered that this is a rash due to occlusion of this, or blockage of the small arteries in the skin. And it made me start thinking, maybe it was the same gene causing both diseases of the artery. So as a physician scientist, I could see these patients, take their samples back to the lab, and figure out what exactly was causing the disease in the family. And we found out that a gene called ACTA2 is causing the disease. And now when we look at this family, we can actually shade in the symbols in yellow for everybody that carries the mutation, and now you can see that everybody who has survived a dissection carries this mutation. But at the same time, you can see there's many people in the family that carry the mutation but have not had aortic disease. So we asked the question, are those the individuals with the coronary artery disease? And indeed they were. So using this family and others, we could conclude that one gene was causing both enlargement and blockage of an artery, with about 10 million to 1 odds that we were correct. The story was even more interesting in other families that had a different change in that same ACTA2 gene. In these families, we saw the aortic aneurysms and dissections, but we also saw early onset strokes, which can be caused by blockage of arteries in the brain. And you can see here that people can even have both diseases in these families. And these are early onset strokes. One girl had a stroke at the age of 16. Another boy had a stroke about the same age and died of a massive stroke 3 years later. So this is a very bad disease. So we published those results, and then I started getting calls from physicians and parents all over the world about these children that I show you here. These children have early onset strokes as young as 3 months of age and have aortic disease that needs to be repaired by the time they're 10, 11, or 12 years old. All these children have exactly the same change in the ACTA2 gene. And as you can see, Sally is one of these children. So as a physician scientist, I can go ahead and take this information. Now we know the cause of the disease in these children, and I can take that back into the lab and start figuring out how to better treat this disease in these children. And we've been working on that and using different model systems. We think we have some drugs that will prevent or at least minimize the strokes in these children, and we hope to be able to take that to a clinical trial in the next few years. So I hope this illustrates how I had to talk to the patients, I had to examine them, but at the same time I had the ability to take it back to the laboratory and figure out what was wrong. Put together all those pieces as to why Sally had such an early onset stroke, even though I wasn't even working on stroke. And that's what physician scientists do. Unfortunately, the number of people that are choosing to become physician scientists are decreasing. In 2013, Francis Collins, the head of the NIH, commissioned a committee to look at the physician scientist workforce, and what they found was the number of physicians choosing to do research has declined steadily in the 10 years before. And that's shown here on this graph. This is a tragedy if we want to solve human diseases. We and myself and some of my colleagues have recently published our recommendations to try to reverse this trend. In addition, the advisory committee for Francis Collins, the director of the NIH, had a meeting in June that had additional recommendations on how to reverse this trend. Now, what can you do? We have to have funding for medical research, and we have to avoid the boom and bust funding that we've had over the past few years. Everybody in Houston knows how bad a boom and bust economy is because that's what happens with the oil industry. And we get people into medical research, and then suddenly they can't get funding for their research, and as MDs, they can just always go and just practice medicine. And that's what they're doing, and that's part of the reason we're losing them. So please call your representatives in Washington and ask them to support the NIH, both the funding for medical research and the training for physician scientists. We need that support if we're going to solve problems like Sally had. It's a great time to be a physician scientist. We have so many wonderful technologies. We have better ways to image disease. We have the electronic medical record to rapidly get data on patients. We have stem cells to regenerate tissues and organs. We have whole genome sequencing and gene editing, but we need the physician scientists to take those technologies and apply them to human diseases so children like Sally can have a long and happy life. Thank you.